Hello, my name is Baron, and I'd like to show you the traditional approach to multiplying two numbers in a base other than 10. In a previous video, I showed you an innovative approach that would work for any base and any size number that would require multiplying the two numbers using only the multiplication facts in base 10. But a lot of people don't appreciate that because a lot of people haven't tried even multiplying two numbers in a base other than 10 before. So I thought it would be helpful to give a little perspective and show the traditional approach. So what we looked at in the last video was 536 base 8 times 457 base. Usually there are two ways or two common approaches out there for multiplying of two numbers that are not in base 10. The most common approach is to convert both of the numbers to base 10, then do the multiplication as you normally would in base 10, get the answer, and convert that back to whatever base you started with. So in this case, we have 536 base 8 and 457 base 8. You would first convert them both to base 10, do your multiplication as normal, and then convert the answer back to base 8. That's the first approach. The other approach is to learn a whole new set of multiplication facts for base 8. Now, most people have learned the multiplication facts up to 9 times 9, 10 times 10 in base 10, and you probably learned them with flashcards back in second grade. Imagine having to do that again for a new base. So today you're going to multiply in base 8, so you learn a new set of multiplication facts in base 8. And then tomorrow you have a problem in base 4, so you have to learn those set of facts. And then on another day you have a problem in base 13, so you have to learn those facts. And so the base neutral multiplication approach doesn't require any of that. But I'm going to go through each of these methods, and I'll probably take 2 videos to get to the second one because it is so complicated. But let's look at the first approach here. So it is to convert to base 10, multiply, and then convert back. So if we have 536 base 8, that literally means 5 times 8 squared plus 3 times 8 plus 6. So the 5 is in the 8 squareds place, and get this a little bit smaller, that's in the 8 squareds place, and the 3 is in the 8 to the first place, and the 6 is in the 8 to the zeros place. So literally this is 5 times 8 squared plus 3 times 8 plus 6. You do the math, 5 times 64 plus 3 times 8 plus 6. You get that 536 base 8 is the same thing as 350 in base 10. Likewise, we can take 457 base 8 and convert it. It's 4 times 8 squared plus 5 times 8 plus 7. And you get 457 base 8 is going to be equivalent to 303 in base 10. So now we have the problem, the original problem, 536 base 8 times 457 base 8, and we change that to 350 base 10 times 303 base 10. And by this point, you're probably thinking, oh my goodness, this is a lot of work. And could you imagine if this was a much bigger base, 13, or a fractional base, or a whole lot of digits? You can imagine that this would be a lot of work. But once you get them into base 10, it's pretty simple. You use the standard algorithm, you pull a calculator out. By the way, most calculators will not multiply in something other than base 10. But once you get it into base 10, you can type it in and you get 106,050 base 10. That is the answer in base 10. But guess what? The problem was in base 10. So this part's kind of straightforward. You convert it to base 10. But the last step is to convert back. And this is where it gets really ugly. I'll be honest with you, really, really ugly. So let's look at the next step. So we have 106,050 base 10, and we're going to convert that back to base 8. Now, there are a couple of different ways to do this, but the most standard approach is to figure out what is the biggest power of 8 that will go into 106,050. What's the biggest power of 8? Well, for that, you need to know what your powers of 8 are. So I'm going to go ahead and help you out and give you the first several powers of 8. You can see here that we have 8 to the 0 power. We always have it to the 0 power. That's the ones place. And then we have 8 to the first is 8, 8 to the second is 64. Most people know those. I happen to know what 8 to the third is because I'm a math person, but that's 512. But to be honest with you, I don't have memorized the powers of 8 after 8 to the third. And so I had to pull a calculator out to make this list. And anyway, 8 to the fourth is 4,096. 8 to the fifth is 32,768. And I always go past the number I'm trying to convert just to make sure I don't miss something. 8 to the sixth is bigger. It's 262,144. It's bigger than the number we're trying to convert. So we know we have everything we need. So once we have our powers of 8, the first step is to ask the question, what is the biggest power of 8 that is smaller than 106,050, the number we're trying to convert? What's the biggest power of 8? Well, the biggest power of 8 is 8 to the fifth, 32,000. And so what we ask is, what would 106,050 divided by 8 to the fifth be? You can put in your calculator, you'll get 3 with some decimal remainders. And you'll remember way back in fourth grade when you learned to divide, before you even talked about decimals and stuff, what you did is you did a remainder. And so I'll just demonstrate on this one. It's kind of ugly, but I'll show you what it looks like. You have 106,050 divided by 32,768. Egads, that's huge. But after a little bit of trial and error, you eventually figure out that, this will go into that 3 times. It won't go into it 4 times. And so now we do our 3 multiplied by all of this. And, 3 times 8 is 24. We carry the 2. 3 times 6 is 18. Plus 2 is 20. Carry the 2. 3 times 7 is 21. Plus 2 is 23. Carry the 2. I'm going kind of fast, but this should be familiar with most of you. 3 times 2 is 6. Plus 2 is 8. And 3 times 3 is 9. Then I subtract and I get this number, 7,746. So that's our remainder. But guess what? We're not done. So what do we do next? We have 3. And so now we go to the next. We start with 8 to the fifth. We now divide the remainder of 7,746 by the next lowest power of 8, which is 8 to the fourth, or 4,096. We continue this process. We just iterate. We just keep going. Well, 7,746 divided by 4,096, it gives you 1 with the remainder of 3650. And then you take that 3650 and you divide by the next lowest power of 8, which is 8 to the third. And this goes in 7 times with a remainder of 66. So you take the 66 and you divide by the next lowest one, which is 8 to the second power. 66 divided by 64 goes in 1 time with a remainder of 2. And the next lowest power is 8 to the first. And now this is the part where people really get a little confused here because, well, 8 to the first power doesn't go into 2. So what do you get when you do 2 divided by 8? Well, 2 divided by 8 is a 0 with a remainder of 2. But that 0 is important. Can't skip it. And so we're going to keep going. And the next and last power of 8 that we have to deal with is 8 to the 0 power. The next thing we do is 2 divided by 1. We get 2 with no remainder. And now what we have here is what we've done is we've converted 106,050 in base 10. We've divided that repetitively by different powers of 8. And what do we get? We get these values right here. This is going to be equal to 317,102, and that is in base 8. And that is the answer in base 8. So just a quick reminder of what we've done so far. We have we started with these 2 numbers we started with the 2 numbers in base 8, and then we converted them to 350 base 10 and 303 base 10, and we get our answer of 106,050 in base 10, and then we convert that back to base 8. A whole lot of work. So I want to juxtapose this against the method that we've been using, which is base neutral multiplication. We got 536 base 8 times 457 base 8 Now, the method I would prefer you to use is not the traditional method, but Bayes neutral multiplication. And so, like I did in the last video, just so you can see this, what I'm going to do is I'm going to make an array, a 3 by 3 array, because this is a 3-digit times 3-digit. And I'm going to do 536 multiplied by 457. Make my array, fill it in. And now what I'm going to do is just straight up base 10 multiplication. 4 times 5 is 20. 5 times 5 is 25. Speed up here real quick. I'm multiplying each of the element of the column values to each of the row values. And when I'm done, I get a filled out area model. And what I'm going to do is I'm going to add up the numbers that are along the same diagonal. 20 is along the diagonal by itself. 12 and 25 is going to give me 37. 24 plus 15 plus 35 is 74. 30 plus 21 is 51, and then 42. Now, once I get to this part, I'm going to, this is the base neutral multiplication right here, the base neutral product, if you will. This is the universal value of the multiplication of 536 times 457 in any base. But now we want to know the answer in base 8. So what I would do is I would take this, starting from the right, is I would divide each term by 8. And whatever I get when I divide by 8, that gets carried over to the next column to the left. And my remainder is that term of the answer. So 42 divided by 8 is 5 with the remainder 2. 2 comes down as in the ones place of the answer. And then the 5 gets carried over to the 8's place. 51 plus 5 is 56. And 56 divided by 8 is 7 with a remainder of 0. 74 plus 71, 74 plus 7 is 81. 81 divided by 8 is 8 with a remainder of 1. Excuse me, that's not true, it's 10. 81 divided by 8 is 10 with a remainder of 1. 10 plus 37 is 47. 47 divided by 8 is 5 with a remainder of 7. 5 times 20 is 25. Excuse me, 5 plus 20 is 25. 25 divided by 8 is 3. 3 times 8 is 24. 3 times 8 is 24 plus 1 is the remainder. And then I bring down the 3. So my answer is 317102. Base 8, exactly what we got in the last method. Now, I'm not going to show you the next part so much in this video, but I'll just describe what it is so you can see. You could use a whole new set of arithmetic facts. Here I've constructed a base 8 multiplication table, and you can see it's different. In normal base 10 multiplication, 4 times 8 is, or 4 times 2, for example, 4 times 2 is 8 normally, but in base 8 we don't have the digit 8, so it's 1, 0, and so forth. And so you could use all these facts and you could multiply it out. Now, could you imagine doing this with this kind of ugly problem? I'm not even going to try to do either method traditionally, a fractional exponent. Here's the moral of the story. Drop those two traditional approaches. They're just way too complicated. Instead, use base neutral multiplication. Hope you've enjoyed this video. Hope it's clarified some things. In the next set of videos I'm going to make, I'm going to scale it back. I'm going to get away from all the base neutral and different bases, and we're going to stick in base 10. We're going to look at how would you teach this to a third grade? How would you teach it to a fourth grader? What elements, where do the decimal or fraction point come in middle school? What's the tie-in to scientific notation? Where does this relate to Algebra 1 and Algebra 2 and polynomial multiplication and even factoring? It's all tied together. I hope you join us. Please subscribe if you want to get the videos as I make them. And thank you very much for your support.